Hello. Now we're going to discuss a thing called L'Hopital's rule. It kind of has a funny spelling. I won't go through. These are some complicated rules to lay it down. You don't need to remember all this. You probably are panicking looking at all this. You're never going to use all this stuff. Uh, the moral of the story is a function has to be two functions have to obey a fairly stringent set of sort of stringent set of conditions for L'Hopital to apply. But usually in ordinary calculus, we deal with nice functions anyway, and usually this stuff is going to be when somebody asks us to do L'Hopital's rule, all this stuff is going to be good right here anyway. So yeah, for L'Hopital's rule, yeah, we're going to let a be less than b. We're going to let c be an open interval ab. We're going to let f be a function from the closed interval ab into r, and g likewise, such that rule 0, f and g are continuous on the closed interval AB, and FC, GC both equal 0. Rule 1, F and G are differentiable on the open interval AB, but not necessarily at C. They're continuous at C, but not necessarily differentiable there. Rule 2, either both limits go to 0 or both limits go to infinity. Of some kind. Either both limits go to 0 or both limits go to one type of infinity. Now, the signs don't depend. Like, it could very well be that the f limit goes to positive infinity and the g limit goes to negative infinity, or they may both go to positive infinity, or a whole Fruit Loop variety. But they'll either both go to 0 or they'll both go to a type of infinity. The signs are independent. Rule 3, g prime will not vanish for x in the open interval, the deleted open interval AB with c taken out. Rule 4, the limit as x goes to c of f prime over g prime will equal L for some real number L, and L will not be infinity either. L will be a real number, okay? So that's a fairly stringent set of conditions, but you don't need to remember all that. So basically, we're only going to apply L'Hopital's rule 9. If all this is true, that's a lot of restraint. Then the limit, if f and g are really nice, then the limit as x goes to c of f of x over g of x will equal the limit as x goes to c of f prime of x over g prime. The limit of the quotient is the limit of the quotient of the two derivatives, in very loosely speaking. Okay, I'm being somewhat loose, but that gets the idea across. The f over g limit is the f prime over g prime limit under, as long as the conditions are ripe. Okay, let's do some. So you don't need to go memorizing all those rules. Please don't. Usually your professor will lay down when you can use L'Hopital's rule. There's one situation when you should not, and that's sine x over x. There's a good reason why you should not do that. It has to do with circular reasoning. The sinc function sine x over x, don't do it there. But you can use it for the cousins of it, like sine 2x over 2x. You can go ahead and do L'Hopital, but don't do it for sine x over x. Don't do L'Hopital there, okay? But we'll talk more about that in a minute. But anyway, let's look at this example. The limit as x goes to 7 of x squared minus 49 over x minus 7. I know what you're thinking. I could just difference the squares factor the top. But let's do L'Hopital, or L'Hopital's method. If this f of x is x squared minus 49, okay? And my g of x is x minus 7. So if I differentiate just the top, if I differentiate x squared minus 49, that's 2x. If I derivate x minus 7, that's just 1. Okay? But then, okay, stop there. Okay, I'm done. Okay, notice that my denominator no longer goes toward 0 as x goes to 7, so you have to stop. So the limit as x goes to 7 of 2x over 1, well, hey, you can plug 7 in directly without getting 0 over 0. That's just 2 times 7 over 1. That's just 2x, guys. That's just 2 times 7. That's just 14. Yeah, sure, I could have just done algebra. You still got to cancel in any event before you can do the limit, even if you would have done algebra. But anyway, but I wanted to illustrate L'Hopital's rule, okay? But let's go to this example down here. Algebra, I can't do algebra anymore. Limit x goes to 6 of the ln of x minus 5 over x minus 6. Guys, if I plug 6 in directly, I would get the ln 1 over 0. That would be 0 over 0. I can't do that. So if I derive just the top guy by himself with respect to x, if f is the ln of x minus 5, okay, just f. F prime would hence be 1 over x minus 5. G is x minus 6, so g prime would just be 1. Oh, that's just 1 over x minus 5 himself. Okay, and then the limit as x goes to 6 of that, you just plug 6 in directly by continuity, and that's just 1. Okay. Oh, that's nice. All right. Now let's look at a more beefy example. The limit as x goes to 2 of this guy right here. Okay. Now we need to get, at first this is messy because we're getting 1 over 0 minus 1 over 0 because the ln of 1 is 0 and 2 minus 2 is 0. We're letting x go toward 2. Now we get a common denominator. We put x minus 2 up here and we put the ln term up here. So x minus 2 up here, ln 2 up here. Back up. X minus 2 up here, the ln of parentheses x minus 1 up here. So we get x minus 2 minus the ln term all over the common denominator down here. Okay, that's good. But the thing is, that's messy though. My next thing I want to do is what do I want to do next? Okay, so I have this guy right here. What's the next thing that I do? Oh, L'Hopital. I let this entire numerator right here. Excuse me. Oh, I just want my numerator, please. Okay. This guy that I have highlighted right here, that's f of x. And this guy down here in the denominator that I don't have highlighted is my g of x. So f prime is 1 if I derivate this, x minus 2 is just 1 when I derivate it. And then I got minus. And if I derivate the ln of x minus 1, that's just 1 over x minus 1. Okay. So here's f. And then here's F, right here where my cursor is now. This is f prime. Alrighty. Now down here was my g right here. Back up. This is my g. Now here is g prime. Remember, you got to do the product rule. I do x minus 2 so I derivate x minus 2 first and leave ln alone. The derivative of x minus 2, that's just 1. So 1 times ln is just ln himself. And then plus, and then I derivate ln of x minus 1. That's 1 over x minus 1. And leave x minus 2 alone, but that just puts x minus 2 upstairs. So I get x minus 2 over x minus 1. Okay. So there's that. So here's g prime. Here, all the stuff here on the bottom is g prime. Okay. So that's equal to the limit as x goes to 2. Now I need to clean this up. I'm just going to do some algebra now. So by common denominator, I'm going to multiply the top and the bottom by x minus 1. So if I distribute x minus 1 through the top, x minus 1 times 1 itself is x minus 1. And x minus 1 times 1 over that x minus 1 is just 1. Right here. And then I distribute x minus 1 down here. X minus 1 times ln is just that. Parentheses, x minus 1 times ln. And then plus x minus 1 times the quotient, x minus 2 over x minus 1, just leaves plain Jane, x minus 2. Because the x minus 1 down here will kill the x minus 1 that I multiplied by distributively. Okay? So now, but hey, see this x minus 1 here and this this negative 1 here and this negative 1 here will make a minus 2. So I have x minus 2 up here. Whew. Okay, so I have x minus 2 over x minus 2 plus x minus 1 ln x minus 1. And by commutativity, I can move this x minus 2 over here to the left. All right, so now the next thing I'm going to do I do another application of L'Hopital's rule. I can turn around, I must. Notice, guys, if I was to plug 2 in now, I would still get 0 over 0. I'm not done yet. I'd get 0 up here. I would get 0 down here because 2 minus 2 is 0. And here would be a 1. I would get 1 ln 1, but ln 1 is 0. So I would get 0 plus 0, which is 0 down here. So I still get 0 over 0. So sometimes you have to turn around and do L'Hopital again. So I turn around and do L'Hopital again. And so I've got to turn this f prime into f double prime. So I derivate x minus 2, and I get 1. I'm derivating, I always derivate in this example anyway with respect to x, or if they give me t, I would derivate with respect to t. It's whatever letter they give you. I'm always using x in these problems, but anyway. So I derivate again. F double prime is 1. Now, x minus 2 turns into 1. And then I do the product rule. Now, remember, I derivate x minus 1 first and leave ln alone. X minus 1 just turns into 1, and that just leaves ln by himself. But that 1 is understood, and I don't even write it. So that's just ln. And then I leave x minus 1 alone and derivate ln. But, guys, what that does is that's going to give me x minus 1 here over x minus 1, because the derivative of ln x minus 1 is 1 over x minus 1. So I have this x minus 1 times 1 over x minus 1, and that just gives me 1 itself, because reciprocals cancel to 1, so I get this 1 right here. Okay, but then after that, these 1 plus 1 is, of course, 2 right here. Okay, so I just did the product rule, and things kind of turned out funny. But I get 1 over 2 plus ln x minus 1. All right. And then now, at last, I can plug in 2. I can't do L'Hopital anymore. So I plug in 2 by continuity. And so I've got 1 over 2 plus. If I plug in 2 here, 2 minus 1 is 1. So I get 1 over 2 plus ln 1. But ln 1 is just 0. But 2 plus 0 is 2. The denominator is okay. You know, that's just a 2 down there. So that's just 1 over 2. 2 plus 0 is 2. So 1 over 2, but that's a half. So finally, my final answer is a half. Notice that was a good deal harder. You know, that took a lot more brain power, right? You know, that was much harder. Whew. So that's L'Hopital's rule. And as you can see, it gets hard. Sometimes you have to apply it 2 times. Sometimes you may have to go as far as, you know, there's examples where you might have to apply it 10 times, you know, but just however many you need to apply it. Now, there's examples where L'Hopital's rule gets funny. Consider this example right here. Consider the limit as x goes to 0 plus of x to the x power. Note that the limit as x goes to 0 plus, we're coming into 0 from the right, because from the left it's undefined. The limit as x comes into 0 from the right of x to the x. That doesn't make sense. That's kind of hard to think about, but that can be thought of, x to the x can be thought of as e to the x ln x. Okay, but there's a rule that says that the limit of e to the power is e to the limit of the power. Okay, so we can bring that limit upstairs. So that's e to the limit, x goes to 0 plus of x ln x. So, but then, now, this is okay, but we want to write it like this. We want to turn x ln x into ln x over 1 over x. And you're like, well, Jason, that's a funny way of writing this thing. Yes, it is. But here's why we want to do that. If I plug 0 in here, I would get ln, you know, as x goes to 0 from the right, ln x goes to negative infinity. And as x goes to 0 from the right down here, 1 over x goes to positive infinity. Okay, so I'm getting infinity over infinity here. So I need to apply L'Hopital. So I derivate ln x up here, I get 1 over x. I derivate 1 over x down here, I get neg 1 over x squared, you know, from the differentiation rules. Okay, But by the rules of exponents, remember the negative can just come out to the side. 1 over x squared on the bottom is really x squared up top. And the 1 over x up top is really just an x on the bottom. And then negative x squared over x, that's just negative x itself. All we have left is negative x itself. So we just have the limit x goes to 0 from the right of negative x itself. But hey, but now we just have continuity. We can just plug 0 straight in, and that's just e to the 0. But e to the 0 is 1. And so, and again, this little comment right here, that was, I wish that little box would just go away. This comment right here in purple, that was when I went from this, early on, when I went from this step right here to this step right here, when I brought the limit upstairs in E a long time ago. But anyway, there's that. And let's look at this example right here. And as you can see, this stuff gets hard. This isn't easy breezy. This is tough stuff. The limit as x goes to pi halves of cosine x over cosine 3x. This would be 0 over 0 if we just plugged it in as is. We differentiate, we do d by dx of cosine x, which is, if we let up, which is neg sine x, and then separately d by dx of cosine 3x, and that's going to be neg 3 sine 3x. But the negatives are just going to cancel each other away. And so, and hey, and now by continuity, we can just plug the pi halves in, because we don't vanish. We must really plug them in. We can't do L'Hopital anymore. And so we get sine, once you stop getting 0 over 0, you must quit L'Hopital, guys. You can't keep going with it, okay? So you get sine pi halves over 3 sine 3 pi halves. But now, that's 1 over 3 times neg 1, because this is sine of 3 pi halves is neg 1, so it's a neg 3 down there. Now 1 over negative 3 is neg 1/3, okay? So there's that example. And here's a word of warning. Don't use L'Hopital to establish the limit of the sinc equals 1. It's circular reasoning. I'm not going to go into all the reasons why. You can use it on the first cousins, though, of sine x over x. Just don't use it on sine x over x himself. It's bad form. It's circular reasoning. But you can do it on variations. Like the limit as x goes to 0 of sine 3x over 2x, it's fine. Go ahead. Have a field day. Let f of x be sine 3x, let g of x be 2x, and do your f prime up here, and you'll get 3 cosine 3x. Do your g prime down here, you'll just get 2. And then you can just go ahead and plug in 0 by continuity. And the cosine of 0 is just 1. And 3 times 1 is just 3. So you'll get your 3 halves. And then in a similar fashion, 8x over sine 3x. Let f of x be 8x and g of x be sine 3x. So f prime is 8. G prime is 3 cosine 3x. And then the buck stops. You got to plug 0 in. That's just 3 times cosine 0. That's just 3 itself. So 8/3. So you can do it on variations, okay? The next thing I wanted to talk about, you can do the limit, we can do it on this. The limit as x goes to negative infinity of a polynomial over a polynomial. 7x cubed minus x squared over 11x cubed plus 8. Really, we'd be better off, this is sort of a horizontal asymptote example, really. But I wanted to amplify, I want to do L'Hopital's rule. We do we let f of x be the numerator, g of x be the denominator. So here f prime is up here, g prime is down here, but we got to keep going because we still get 0 over 0. We do another iteration, or no, we get infinity over infinity, excuse me. We do another iteration, but we still got to keep going because we still get infinity over infinity. So we keep going. Aha. So finally, we get that. Well, no, I got to stop the video. I'm out of time. Let me finish this on the next video. So hold that thought. I got to finish this on the next video. Hold that thought. I'll see you on the next video. I'll finish this example. Bye.